All right, ladies and gentlemen, welcome back to the last installment of your favorite class. Yeah, guys, getting near the end. Most of you seniors, I guess, it's probably the last installment of any class of yours that's held. So, congratulations, those of you that are graduating. That's awesome. Wish we could all be together to sort of celebrate, but it is what it is. Right. So today we're just gonna do a final exam review, and then Friday is your final exam. If you didn't know that, what have you been doing? All right. I like the meme today. So Ian submitted this along with his homework. When you know it's the last time you're gonna hear him say "rar," oh, it's gonna be a sad "rar." Rar. Okay. The little kitty cat. Right. So final exams on Friday. The study guide has kind of been posted, and that's what I'm gonna go over today. So the exam will just proceed like the last one did. Show up a couple minutes early. You'll do it by hand. And then when you're done, scan it in and submit it. All right, everyone's doing great in this class. I'm actually really proud of the way that you guys have continued to do your homework and stuck with the class, and no one's dropped, and everything's just been as smooth as could possibly be given the situation. So proud of you guys and how you've handled. So finish it up strong. Just make sure you look over the stuff from the study guide and know all the information there, and you'll be right as rain. All right. So without further ado, let's do it. Dang it. All right, so I've copy and pasted the study guide from this document here to OneNote, so I can kind of like go through it. Okay, so this document here is on Blackboard. It has all the information I think you should know for the final exam. All right, so here we are with your final exam study guide. And so we're just going to run this down as kind of as far as we can go, and then I'll let you go and set you free. So first thing we did after the last test was talk about Keir kinetics and real logical models. So let's get on with that. Know the definition of Keir kinetics? All right, so kinetics is a pretty well understood branch of chemistry. It's a study of rate of reaction. If you want to throw Keir in there, then maybe we come up with a little more formal definition that's something like, I don't know, I'll just come up the top of my head. The study of rates of reaction. For thermal setting. Materials. That seems like a pretty good definition. You have to include somehow that the chemical reaction is including a Keir step, right? That's what we mean by like Keir kinetics, the study of the rate of reaction of something that is going through a Keir. All right, so pretty straightforward. Just understand and know what people mean if you walk by someone and they're talking about Keir kinetics or say that word, you understand. All right. Now, for epoxy chemistries, what do the Keir kinetics depend on? Which effects are most important? Well, they depend on many things. Obviously, time, temperature, pressure. The things that we kind of like control in the manufacturing process. Those are the three big ones: time, temperature, and pressure. It also might depend on if there are other chemical species present. So, do you have accelerators? Do you have inhibitors? All right, we didn't really talk much about accelerators and inhibitors, but if you're talking about the rate of reaction of an epoxy, usually epoxies will include some tertiary component that is like a dilutant or an accelerator or an inhibitor. And what those typically will do is either slow down or speed up the reaction. And most of the time when you're talking about composite processing, you want to slow down the reaction because if you mix part A and part B, you want a longer time to manufacture your part, okay? You want a working life or a cure time of, many hours, so that if you're doing a Vardam infusion or RTM or doing the vacuum bagging, autoclaving, so on and so forth, you have enough time to do what you need to do. Okay, so there are other things that are there. The most important in all of this, obviously, is the temperature. All right, so the rates of chemical reactions are Arrhenius with temperature, they're exponential with temperature, so temperature plays a more important role than anything else when it comes to chemical reactions, except maybe if you have some crazy accelerators could provide a little bit more interesting phenomena. But temperature by far is one that is used in every chemical reaction, and it drives every chemical reaction. All right. Practically speaking, why are they useful? Well, they can give you important information about your process. All right, gel time, total curing time, etc. Gel time, total time. All right. It's also useful if you're looking at doing secondary bonding. So if you need a composite that's at like 90% cure, you need some sort of model that tells me, all right, at this time and this temperature, it's going to be cured at 90%. And then when I go to a secondary bonding operation, I know I have 10% of my moieties left to react. All right. So secondary bonding. Bond. Secondary bond. All right. What is the chemical structure of an epoxide moiety and an amine moiety? All right, I'll give myself a little more space to do this. So remember, a moiety is a chemical species which is going to participate in the reaction. So epoxide moiety, that's OCC, or sometimes just drawn as that. So that's the epoxide moiety, and then the amine. Usually this is, connected to some random R group, okay? Your amine moiety is the NH2, so NH2, and this is connected to some other portion of the molecule. All right, so this is your moiety here. This is reacting with this, and the way that this works is one of the hydrogens from the amine will pop off and spring open the epoxide ring, and there you go. That's how that kind of works. All right, so there's your epoxide and your amine moieties. All right, what is the full name of the chemical epoxy chemical reactant? All right, that's Digiba, right? So Digiba for short. D-G-E-B-A is the most common, and this is diglycidyl ether of bisphenol A, obviously. Not to be confused with diglycidyl ether of bisphenol F, which is also a very common chemical reactant. Know your Digibas. All right. What is degree of cure? How do we use heat of reaction to calculate degree of cure, and what scientific instrument is commonly used to track heat of reaction? All right. What is degree of cure? All right. So degree of cure is probably best to explain mathematically. We typically denote degree of cure with the variable alpha, and it's a ratio of how much heat has been released by my reaction divided by the total heat the reaction could release. All right, sometimes this is written as Q over Q total. All right, so there's your degree of cure. It ranges from value 0 to 1. 0 meaning I have not reacted at all, and 1 is I'm completely fully reacted, I've extracted, or all of the heat has been released from this particular reaction. All right, so that is degree of cure. How do we use heat of reaction to calculate degree of cure? Okay, well, that's here, the heat of reaction divided by the total heat of reaction to calculate degree of cure. And what scientific instrument is commonly used to track heat of reaction? Well, that's a calorimeter. The most common in industry is for evaluating this is called the differential scanning calorimeter, or DSC for short. But generally, if you want to track the heat of a reaction, you're looking for a calorimeter is the general name. All right. What is the rate of reaction? All right, this is different. So let's talk about rate of reaction. Rate of reaction is d alpha dt. This is rate of reaction. It's how fast or slowly the degree of cure is changing. All right, so it's the derivative with respect to time of the degree of cure evolving over time. All right. Why do most rate reaction models depend on the degree of cure? Right. So usually d alpha dt is some function of alpha, right? So why does the rate of the reaction depend on the current degree of cure of the reaction? Well, we talked about this. As epoxies cure, there are less and less moieties available for reaction. Okay, so if I'm an epoxide moiety and I'm looking for an amine moiety to mingle with, all right, I'm single, I'm ready to mingle. If I'm looking for amine moieties around me, if my degree of cure is 0, then every single amine moiety around me is available for reaction. All right, if my degree of cure is 0.99, meaning I'm almost fully cured, there are basically 0 free amine moieties around me to participate in reaction. So the reaction will proceed a lot faster if all of my neighbors are available to mingle, rather than if there are no neighbors available to me to mingle with. Okay, so it depends on degree of cure because molecular interaction, more or less. So why do rates depend on degree of cure? Molecular interaction. I'll say molecular availability. If there's no one available for you on Match.com, your rate of reaction very low. Okay. What else does the rate of reaction depend upon? Well, there's a lot of things there, but temperature is probably the biggest. All right. No nth order and general rate equation for epoxy cure kinetics. All right, so remember our rate equations. We had something like d alpha dt equals k1 minus alpha to the n. That's your nth order rate equation. And then the general rate equation is a little bit more complicated than that. I don't know if I'm going to have the space to put it in here. This is k1 alpha minus 1. I can't quite remember it off the top of my head. It's in the notes. I don't want to make sure I don't mess it up. I'm old, okay? Leave me alone. All right. K1 plus K2 alpha to the M multiplied by 1 minus alpha to the N. There's your general nth order rate equation. All right. All right, the general rate equation. This is nth order, this is general. All right. How is the rate constant K related to temperature? All right, it's a Arrhenius relationship. So what I mean by that is K equals AE to the KT, right? Or AE to the RT, where R is some rate constant. All right, so it's Arrhenius with temperature, meaning it's exponential. All right. What is a secondary bonding technique? What are some examples and how are secondary bonding techniques related to cure kinetics models? All right, second bonding techniques we talked about is like co-curing, generally secondary bonding, co-curing. What are the other technical terms? Co-bonding, bonding, co-bonding, etc. And the idea here is that if you have laminate number 1, which is cured at alpha equals 0.9, and you have another laminate that you're going to bond to it, if alpha equals 0.9, and you bond these guys, then you get increased reaction at this bonding site, okay? And that's because there's a chemical reaction that occurs across that interface rather than just like an adhesive reaction. All right, so there's cohesive reactions as well, meaning that the molecular structures of the two different species are interacting with each other. All right, so what is a secondary bonding technique? What are some examples? How are they related to cure kinetics models? Well, they're related to cure kinetics models because if you want 90% cure bonded to 90% cure, you need to know what temperature, pressure, and processing conditions get you to 90% cure. All right? Awesome. Let's continue. What is viscosity? Technically speaking, the viscosity is the ratio of the shear stress to the shear strain rate. Okay, so technically speaking, I'm running out of space here. Man, I need more space. So technically speaking, viscosity is the shear stress that you put on the piece, tau divided by the strain rate, gamma dot. All right, this is your viscosity generally. Physically, it's how much the material flows given an applied shear stress. All right, so that's your viscosity. What scientific instrument is typically used to measure viscosity, and how does it work? All right, so that's a rheometer. All right, rheometer. We talked about rheometers a little bit here. I'll just bring the picture in really quick. But basically, you put like a spindle inside of the liquid, and the spindles are a variety of different types. I mean, there are many different types. And the amount of torque that it takes to spin the spindle inside of that liquid, the amount of force, the kind of like moment required to spin that spindle, gives you an indication of how viscous the material is. The more viscous it is, the harder it is to spin that thing at a certain strain rate. Right? So you can measure the torque, and you know how fast you're spinning. So you have shear stress, you have shear strain rate, and the ratio there is the viscosity. All right, so that's how a rheometer works, and this is one in action. This guy here, so you see kind of like the doors here that are open, those kind of close shut, and inside there's this like oven chamber that the spindle goes if you want to do things like change the temperature inside of there and see how the viscosity changes, those sorts of things. All right. Next, what does the viscosity of a recently mixed chemistry depend upon? Assuming Newtonian fluid. Again, temperature is the biggest. All right. So temperature, temperature, temperature. Sunday, Sunday, Sunday. All right. Practically speaking, why are viscosity models useful? All right. Viscosity model is useful because, again, it could give you gel time. All right. So again, it's like this working time. It tells you when the viscosity is going to shoot up to infinity, and you're no longer able to process the material. That's probably the biggest one. Also, it can sometimes be useful for sizing pumps. So if you need to know how strong your pump needs to be to pump in your liquid into your RTM process, you need to know the viscosity of the fluid, because the more viscous it is, the more back pressure you're going to get from like trying to pump the fluid through some sort of pipe or something. All right, so that was a lot there. Now, calculation type questions I might ask you. Determine degree of cure using a rate of reaction model. So we did an example of this type of calculation in class, and you also had one on your homework, where you determine degree of cure using a rate of reaction model. Okay, so I might give you something like the nth order reaction model, which looks something like this, and ask you to integrate that and solve for time and determine what is the degree of cure as a function of time. So that's something that I asked you to do on your homework. So that's not an unreasonable thing to do in a short amount of time. All right. Estimate the degree of cure given heat flow of a sample as a function of time. So this one's a little bit more subtle. But remember what heat flow as a function of time looks like. So here's time, here's heat flow, usually given as WT in watts. Usually watts or watts per gram. And this comes from a calorimeter. And what this looks like is you're heating up, heating up, heating up, and then over time the heat of reaction kind of tapers off, something like that. And so this is the total heat of reaction. Total heat. And if I'm interested in what is the current degree of cure of this piece at any time t, well, at this particular time, let's call it T1, I would move my way up here and say that this is the heat associated with time T1. So this is Q at T1. And then my degree of cure, alpha, would be whatever Q is at time 1 divided by the total cure, right? So if I gave you a graph that looked like this, you'd have to, what is the area under the curve for the total situation? What is the area at some specific point, so on and so forth, right? So you should be able to calculate degree of cure given some sort of general chart that looks like this. All right. Estimate the gel time of resin given experimental data or information about the viscosity model. All right, so viscosity models, and what you'll see coming out of a rheometer looks kind of different than what we have here. out of a rheometer. Here's your time, here's your viscosity. And so usually for a rheometer, your data will look something like this. You have this flat line for viscosity, slightly increasing, and then all of a sudden, bang, up to infinity. And beyond, right? And you might have another data set that's at a different temperature that shoots up to infinity here. And this might be T2, and this might be T1, and obviously T2 greater than T1, because we know that viscosity depends on temperature, and it's going to shoot up to infinity very, very quickly at higher temperatures of cure, right? So there you go with some rheometer type data. All right, so if I give you that sort of thing, you might want to estimate the gel time as like, I don't know, the time that it approximately goes to infinity. So here's like T gel for temperature number 1. All right, where does it shoot up to infinity? Give me some approximation. All right, so that's that. Next, we went on to fracture. All right, and fracture was, this portion of the course, probably the most mathematically intense part that we kind of had, though I think fracture is important for composites because it's like one of the dominating modes of failure, right? So important for you guys to know fracture. That's why I spent 4 or 5 lectures on it. All right, able to sketch the 3 fracture modes. Yes. All right, let's do that. All right. Mode 1. Here we got our awesome sample. Here's the crack. Mode 1, here. All right. Mode 2. Here we got our crack again, would be loading this general direction. And then mode 3. I expect this level of terrible sketching on your test, okay? Mode 3 is we're loading across the plane, this way, this way. All right, the trouser tear. Not the trouser terror, the trouser tear. All right, those are the 3 modes. Understand the energy balance associated with external loading of solid materials and how we use this to calculate the energy of a single fracture. So we know generally when we load a solid material, let's say you have some bar, guy walks into a bar. All right, so let's say we have some bar and we're loading this up, just in uniaxial tension. Well, there is a work associated with us providing this external force. All right, so the work of external forces is going to be something like the integral of this load over the displacement integrated over the displacement. All right, so there's some total work that gets applied to this piece. And the total work that we apply externally has to be balanced by the work that, or the energy that's inside of the piece. All right, could be balanced by elastic strain energy, could be balanced by plastic strain, could be balanced by motion, so kinetic energy, and it could be balanced by fracture. I'll also say other. Other might include things like heat, sound, those sorts of things. All right, if I load very quickly, it's going to make a noise. That noise is release of energy. All right. Now, what we talked about with our class is we generally said that materials were brittle. So we're kind of neglecting this guy here, saying that we're brittle. All right, so we don't have any plasticity in our samples. That's an assumption that we made. If you make a thermoplastic composite, that's not a good assumption. Okay. We're also assuming it doesn't move, so no motion. Other, so we're neglecting. And so really, the total work that we put into the system, we said was going to be balanced by elastic strain and by fracture. So mathematically, we wrote that the total work that goes into a piece is the elastic strain energy UE plus the energy associated with fracture, which we labeled as capital D. All right, so this was the general model and where we built everything for composites in our particular class. This was the basis for all of the modeling that we did for our system. All right, so kind of just understand this generally and why we have to assume something like a brittle material so that we can neglect plastic strain, and why we have to assume that we're loading it slowly so that there's no energy and kinetic energy, etc. Right? How we use this to calculate the energy of a single fracture event for a brittle material. All right, this again goes back to what it looks like when we load one of these things up. So here's like my displacement delta, here's my load P, and let's say that I have a sample that looks something like this, and I'm pulling on it here, and it's got a fracture there. All right. So what's going to happen if I put this in a load frame? It's going to load up, and then all of a sudden, at some point, there's going to be some fracture event, bang, that occurs. And that fracture is going to release the energy, and then we can unload back to the beginning. All right, so this is load, and this is unload. And here, this is the fracture. All right, so the energy that we recover is the energy inside of this triangle here. This is recovered energy, which is the energy under the curve here. So this is elastic energy, UE. And then the energy that went into the fracture is the remaining energy that exists inside of this load displacement curve. All right, so here, this is the energy of fracture, capital D. All right. So if the crack advance, this delta A, has the energy associated with, which is this capital D, then we say that the critical strain energy release rate, which is GC, is just equal to fracture energy D divided by the crack advance length delta A times the width of the piece into the page B. All right, so we assume that this has some width to it, which is little b. All right, so this is your critical strain energy release rate. It's in units of something like joules per meter squared. Energy required to open the crack a certain area, right? Energy per crack opening area, joules per meter squared. And that's your fracture of a brittle material. All right, so what is critical strain energy release rate? Well, I just talked about that. Why does our theory require the property to be purely elastic? Response to critical strain energy release rate appropriately. All right, so we talked about it being brittle because we know that it has to be just elastic strain and fracture that sort of balance this thing out. So we have to have brittle behavior so that we can eliminate plasticity. All right, so brittle, no motion, eliminate plasticity, eliminate kinetic energy. All right. So that's why our theory requires the material to have a purely elastic response. All right, next. Understand the difference between current crack length and change in crack length, and when to use which for calculation of fracture toughness. All right, this kind of threw you guys a little bit in the homework. A lot of people sort of had this mistake differentiating between total crack length and crack advance. All right, so say you have some sort of fracture specimen. Let's call it a double cantilever beam specimen. And here's my initial crack length, and I'm loading this guy up here, right? This is a double cantilever beam composite specimen. It's got width into the page of B. All right, so I load this guy up, and I'll say that it has some initial crack length, which is a 0. All right, it's my initial crack length. Okay, when I load this thing up, let's say it behaves in sort of like a stick slip fashion. So I load this guy, it fails a little bit, I load it more, it fails a little bit, I load it more, it fails a little bit. All right, and then we unload. All right. So what that's going to look like is I'm going to have a failure event here that occurs, a failure event here that occurs, and a failure event here that occurs. All right. So the crack is going to propagate in each one of these situations. All right. Maybe that's the propagation associated with event number 1. There's some propagation associated with event number 2, and there's some propagation associated with event number 3. All right. The change in crack length between let's say this point and this point is this length here. This is like delta A for crack propagation event number 1, right? It's the crack propagation associated with this first discrete event, right? That's different than the crack propagation associated with event 2. Okay, so that might be from here to here. So this distance is delta A2, distance that the crack propagated for event number 2, associated with that point and that point, the amount that the crack opened between those two particular points, so on and so forth. That is different than the total crack length, which, let's say at this particular location, the total crack length would be this guy here. All right, this is A2, where this is sort of the second propagation event. This is A2, so what is the crack length at this location? All right, so know the difference between total crack length and crack propagation between two different points. They're different values, right? All right. What sample geometries are commonly used to evaluate mode 1 fracture toughness? All right, well, double cantilever beam for mode 1. So if you're looking at it from the side, it looks like this. You have some starter crack, and you're going to load it here and here by maybe you put piano hinges on there, maybe you drill some holes inside of the sample, something. All right, so this is mode 1 double cantilever beam, and then mode 2 is the end notch flexure. Abbreviated as ENF. All right, and the edge notch flexure looks very similar to a double cantilever beam, except in the way that it's loaded. All right, so here again we have some pre-crack that's inside of the sample, and now we're going to load this guy, typically in 3 or 4 point bend. All right, so P on 2, P on 2, and P. That's going to cause this crack to propagate in that general fashion. All right, so that's edge notch flexure. All right. What is plotted in the resistance curve of a fracture specimen? All right, well, the resistance curve of a fracture specimen plots GC versus crack length delta A. All right, what is fiber bridging, and how do I identify fiber bridging in resistance curves? All right, need some more space. Might be better just to show the picture of this guy. Picture's always better. It's tough for me to like draw fiber bridging. Not so easy to draw. All right. All right, whatever. What note's being dumb? Well, it's probably user error, but you get the idea. All right, here's fiber bridging. You're pulling this guy open, pulling this guy open, and there's all these like hairs that are occurring inside of the crack plane. All right, and those hairs are acting to like toughen the interface between the individual layers. Now, when you first start the testing, those hairs are not there because there's a piece of Kapton or Teflon that's inserted between the layers that stopped that fiber bridging originally. So what happens when you're looking at the response of a test is if you're looking at the R curve for a DCB, it might look something like this. Or here on the x-axis, this is your change in crack length. Well, let's be more precise about this. The crack length AI, and this is your GC value. And you might see something like, all right, initially the values are low, but then at some point it sort of like plateaus off. All right. So what's happening here is that here we're establishing fiber bridging. Okay, so we're establishing something that looks like this. And then once I've reached this plateau here, I've got an equilibrium between the amount of fibers that are being created as the crack propagates and the amount that are being ruptured sort of on the back end there. All right, so like there are guys over here on the left hand side that you see are being ruptured as the crack is sort of propagating, and obviously we're forming new bridges on the front end here as the crack propagates. So once there is an equilibrium between how many we are losing on the left hand side and how many are reforming on the right hand side, until that equilibrium occurs, we're not going to reach a plateau. But once it does occur, then you see this equilibrium in the R curve. All right, so that's how we identify fiber bridging, and that's what fiber bridging is. It's fibers across the interface which help toughen the interface there. All right. Next, be ready to list and describe various toughening mechanisms used to increase interlaminar toughness. All right, we talked a lot about these. There's a lot of different types that we saw. And the list here is on slide 23 of your notes. So fiber bridging is one natural toughening mechanism, but we also talked about all these guys. Matrix modifications, stitching, Z-pinning, interleaving, fibril architectural modifications. All right, so here's like a rubber toughened epoxy matrix. We talked about this picture a little bit. Rubber toughening can help you increase the toughness of the matrix material with all these plasticity mechanisms that are good for rubber toughening. We talked about stitching and Z-pinning. So here we had that gun that was like driving the pins into the fabric. Right? All right. And so we see the pins kind of forming inside of the fabric, but we know that these pins disrupt the fabric architecture that's sort of in the plane. So it's not always the best method. Here we talked about interleaving. So interleaving is using a thermoplastic layer between fabric layers to increase the toughness. So if you add a very thin thermoplastic layer between the individual lamina layers, then you can arrest crack growth through the plasticity that's kind of involved in that thermoplastic interlayer. Okay, so here this is a PA veil. PA is polyamide, which is another name for nylon. Here is PET, polyethylene tetraphthalate, which is a different type of thermoplastic that is going in between layers of a DCB. So you see it sort of toughening the matrix. We talked about 3D composites. The through thickness toe really helps to increase the interlaminar toughness of these 3D composites. All right, so woven architectures giving you this added benefit of increased fracture toughness. All right, so those are some of the toughening mechanisms that we saw in this class. All right. Calculation type questions. Given a low displacement curve of a brittle DCB fracture specimen and dimensions of the specimen, be ready to calculate energy loss to fracture. All right, so I sort of sketched that out before. But the idea there was that if you have some load and displacement curve of some fracture specimen, let's call it a DCB specimen. Here's delta, here's load. You load this up, there's a fracture event, and you unload. You can be ready to calculate what is the area associated with a fracture. So here's D. And then if you have sample dimensions, then G is just D divided by delta A, the crack advance, multiplied by the width of the sample B. So that would be like a sample calculation that might be something you could do on the test. All right. It's areas under the curves, man. That's all it is in this class, I guess. All right. Be ready to calculate mode 2 critical strain and release rate given information about an ENF specimen. So that's something that you did in homework 6, problem 3. So we had an edge notch flexure specimen. There was an equation associated with that. And you did that for problem number 3 in your homework. All right. So that's the fracture section. Woven composites, we just got done kind of working our way through this. You just did this on your homework, so I'll spend a little less time here. What does it mean for a composite to be a woven composite? Well, it has fabric that is interwoven. With multi-directionality. All right. Be able to sketch some 1D, 2D, 3D fabric architectures. We saw a lot of these different fabric architecture types. Hopefully you can sort of sketch them at this point, but the general figure that I had for the class was something that looked like this. So 1D, obviously, this is unidirectional. 2D architectures, we have your bidirectional weaves, which are like plain weaves, satin weaves. You've got knitted fabrics here, kind of on row number 2, and then you have braided fabrics, row number 3. Here are 3D architectures, orthogonal weave, angle, interlock weave, etc., etc. All right, so those are some fabric architectures. How are bidirectional woven fabrics made? Well, they're made on a loom, right? And maybe just kind of be able to like sketch the process. You don't really have to know all the nomenclature, but basically you got warp toes that are being separated, coming together on the back end. All right, so fabric. And then you're passing in between the warp toes a weft toe. And then here, this gate is sort of like lifting up and down the warp toes as he goes through. All right, so this is called the shed. All right, and the shed is kind of arranging the patterns. So I showed a video of this in class. All right. What's the difference between a warp and a weft fabric toe? Well, the warp toes are the toes that are aligned longitudinally, these continuous toes on the loom. The weft toes are being shot in between the openings inside of the loom as it goes through. So that's the difference between warp and weft. All right. Do bidirectional composites typically have the same properties in the warp and weft direction? Why not? Okay, they typically do not. All right. When you did your homework, hopefully you found that it was more difficult to find fabrics that have the same properties in both warp and weft. That's because the way these are manufactured, it's really difficult to actually keep the warp and the weft counts consistent. What I mean by that is you have a certain number of ends, you have a certain number of picks, which are like the warp and weft counts per inch of the fabric. It's really difficult to keep those consistent from a manufacturing perspective. All right. So it's difficult to actually have fabrics with the same properties in both directions, both the warp and the weft directions. All right. Why not? Manufacturing difficult. It's difficult to keep that consistent. All right. So generally comparing 2D and 3D woven fabrics meant for composite manufacture, which are more expensive to manufacture. Obviously, 3D fabrics are more expensive to manufacture. There's only a handful of looms in the world that can make 3D composites, 3D orthogonal woven composites. So 3D orthogonal woven composites, very expensive to manufacture. Have better drapability? Well, 2D fabrics have significantly better drapability than 3D fabrics. That's because they don't have this through thickness toe to sort of like bind them in a similar fashion. All right, 2D fabrics are much more drapable than 3D fabrics. All right, can be used in a wider range of processes. Well, obviously that's 2D. All right, so 3D composites are just much more restricted in what they can do. All right. Generally comparing the composites now, not comparing the fabrics, made from 2D and 3D woven fabrics, which have higher impact damage tolerance, 3D, because they have the through thickness toe, higher critical strain energy release rates to fracture, 3D, at the through thickness toe, have better in-plane properties, that's 2D, because you don't have to account for the fibers that have been pushed to the side by this 3D toe. All right, you got all the fibers in the plane for 2D, so it's much better. Have autoplane properties that are better, 3D. It's because you have the third toe going through the material. Have better higher volume fractions. Well, that's 2D because there are less interstitial regions. And if we go back to the picture of the 3D composite fabric architecture, we can kind of show what this really looks like. So here's the patent for the 3D woven composite material, and they even say right down here empty pocket, resin in composite. So that is an interstitial region in the 3D weave of this particular material. Okay, so that interstitial region gives you a place where epoxy is going to be where there's no fibers. All right, so a lot of interstitial space. You can see it in like the unit cell here too. There's just a lot of like empty space in this unit cell for a 3D woven composite where the epoxy can fill that fibers won't be. All right, are better at resisting out of plane shear loads. Well, that's 3D because they actually have some thickness to them, and they have this toe that sort of holds them from being sheared in this like general direction if it's thin. All right, so calculation type questions. Well, you just did a problem that looked a lot like a calculation question you might have, like example problem 3 from homework 7. Probably not going to ask you a calculation question for woven composites because they're complicated. All right. Last thing for sandwich composites, which is what we just got done doing the last kind of 2 lectures. I really only have qualitative type questions for you guys for sandwich composites. I'm not going to ask you to do any calculation because calculation for sandwich composites, complicated. Why is that? Because we have to account for shear, and our classical lamination theory does not account for out of plane shear. All right. What types of loading are sandwich structures most suited to handle? Well, they're best in bending. Bending, A+. Tension, B. Shear, F. All right, so there you go. What is the method of transformed sections? How is that applicable to a sandwich structure? All right, the method of transformed sections allows us to replacement of different stiffness materials. With same material, but thinner. I wish I could do that. I want the method of transformed section on my stomach line. Okay. All right. So the idea here is if you have a composite sandwich structure, it's got face sheet here, and a core here. You can transform this section if your core is n times less stiff than the face sheet. You could transform it to be all one material that looks like an I-beam. All right, so now it's all face sheet material. And we've reduced the thickness of this by a value of n, where n is the ratio of the modulus of the face sheet to the modulus of the core. All right, so these two behave identically in bending. That's the method of transformed sections. It's applicable to sandwich structures because, well, there you go. There's a sandwich structure that's been transformed. Now it looks like an I-beam, and you know as an engineer that I-beams are generally very good in bending. All right, which laminate stiffness matrix is most infected by incorporation of this stiff core layer? The D matrix. The D matrix relates the amount of curvature that you see in your piece to the bending moment that was applied. All right, so the larger the D matrix is, the less curvature you will have for the same applied bending moment. All right, we know that from our classical lamination theory, and that actually doesn't change with sandwich structures. All right, what type of loading must we account for and consider with sandwich structures? Out of plane shear. Oh my God. All right, so the picture you should have in your mind is with our typical composite laminate that was thin versus your sandwich structure. Which is thick. This guy can't handle loads that look like this. All right, it can't handle these shear loads. Can't do it. This guy, because it has some thickness to it, now those loads can be handled. All right, it can handle those types of shear, and it has a big influence. It's a big deal. All right, it completely changes our classical lamination theory. All right. Know the 4 common techniques for manufacturing sandwich composites? That's in your notes. Where are they most likely to fail? It's the interface between the core and the phase sheets. And what test is commonly used to evaluate shear properties? Short beam shear test. Okay, I made it through. Thank you for coming. I've enjoyed teaching this class. I've enjoyed having all of you. Congratulations to all of you that are graduating. It's very exciting. It's a great class for me. I have passion about composites. I'm very excited to teach this class. And because of the quarter to semester conversion, I don't know if this class is going to make it. So this might be the one and only time this class gets taught, which, it's too bad, but, that's life. Thanks for being part of the class. Come early on Friday. Do your instructor evaluations. RAR. I'll see you then.